Hello. Today we're going to start a new chapter, Chapter 4, Applications of the Derivative. We discussed the derivative in Chapter 3, so one of the questions to ask is what can we do about them? It turns out that we can do a lot of things with the derivatives. We're going to talk about the applications of the first and second derivatives in this chapter, and we start from application of the first derivative in 4.1. We consider 5 different situations of the graph of function f. On the left, we got the increasing function f, and if you draw the tangent line, it's also increasing, and the slope of tangent line is positive. That means the derivative is positive. So we conclude that the function has a positive derivative when it increases. In the second graph, the function is decreasing and the slope of tangent line is negative. So when f decreases, we get negative for the derivative. In the third case, we got horizontal tangent line. So the derivative is 0, or the slope of tangent line is 0, and we got the maximum at x equal to c. In the fourth case, again, we got the horizontal tangent line, and the derivative is 0, but and the function has a minimum this time. In the last case, again, we have a horizontal tangent, but the function f does not have any extrema at the x equal to c. So we can use those information to determine increasing and decreasing of a function. And we follow 4 steps. Step 1, find all critical numbers. The definition of a critical number is where the function has a 0 derivative, or the derivative of the function does not exist. Step 2, we can use the critical numbers to identify open intervals of the domain of the function. Step 3, we test the sign of the derivative of the function in each interval and decide whether the function is increasing or decreasing. And in the last step, we can identify extrema of the function from the information from step 3. And this method is called the first derivative test because we only use first derivative to find the extrema of a function. Let's do a simple example. We got a function f equal to 2/3 x cubed minus 2x squared minus 6x minus 2. And we need to find the intervals where function f is increasing and the intervals where f is decreasing, as well as the extrema of the function f. So this is the polynomial function, and it is differentiable for all real numbers, and the domain of the function is all real numbers also. So we don't have to worry about the case where the derivative does not exist. So by the definition of critical numbers, we just set the derivative equal to 0 and solve for it. So that's step 1, find all critical numbers of f. So the derivative of the function is 2x squared minus 4x minus 6, and we set that equal to 0. So we can factor the left-hand side to get 2 times x plus 1 times x minus 3. And we get 2 solutions, x equal to -1 and x equal to 3. So there are 2 critical numbers. And these 2 critical numbers will divide the domain of the function into 3 regions, or intervals. They are -infinity to -1, -1 to 3, and 3 to positive infinity. So in step 3, we're going to test the sign of the function, derivative of the function at each interval by picking up a specific value in each interval. So for example, on the interval from -infinity to -1, we can pick x equal to -2. You can also pick -3 or -5 or any other numbers in this region. So plug in -2 for x in the derivative of the function. We got 2 times -2 plus 1 times -2 times minus 3. So we got 10. So this is positive. So f increases. In region -1 to 3, we can pick 0 for x and plug in the derivative function. We got 2 times 0 plus 1 times 0 minus 3, and we get -6. So this is negative, and the function decreases. In the last region, from 3 to infinity, we can pick x equal to 4 and plug in to the derivative. We get 2 times 4 plus 1 times 4 minus 3. And again, we got 10. That's positive, so f increases again. So in step 4, we use the information from step 3 to find the extrema of the function. We start from drawing a horizontal axis. And we mark the two critical numbers on the x-axis, -1 and 3. And we draw 2 vertical lines through those two critical numbers. And that would divide the whole domain into 3 regions, as shown in the graph. On the left region, we got the positive for the sign of the derivative, as we already did. In the middle region, we got the negative for the f prime, and in the third region, on the right, we got the positive for the f prime again. So the function increase on the left, and decrease in the middle, and increase back again on the right. So you can see the function attains maximum at the x equal to -1, and attains a minimum at the x equal to 3. So that's this first derivative test. We're going to talk about 4.2 next time.